Good afternoon, Professor.
Good afternoon. Thank you, Marissa. Good afternoon. And I'm laughing because just as you were saying that, I saw Andre. Okay, good night. Yes, that's good. Fair enough. And good night. This has been great. Thank you. We'll be here all week. Okay, no, sorry. Oh, okay. So I'm laughing. God, I love this class. All right. Uh, Thank you, Marissa. Good afternoon. You win on that score. Thank you, Andre, or good night to you. And fair enough, Yabo. And yes, I wonder today might be the day. Thank you. That was a helpful way to. Okay, I'm going to stop talking. But yes, that was a good way to do that. Good afternoon, Jenna. I like that too. Whoa, it's like we're getting to. And by the way, okay, no, I'm getting too excited. Why am I so excited? Okay, but and this is also a reminder, people who still don't think that it counts to write that I hit below in their game assignments, like this is why it does count. Like just the fact that you're like all now like saying it faster than me and saying it in such varied ways, like it's half the class as far as so anyway, okay, I'm thrilled. Oh, but there's people, I'm sorry, hold on. How many multitaskers does it take to have ADHD? No, wait, okay. We start again. And yeah, I do want to do things today, believe it or not, but and the FPD might happen. That's good. I'm going to try to do the FPD thing today, but if I don't do that same reminder again next time, please. That's great. Okay, I'm going back to good afternoon, Jenna. Good afternoon, Kimberly. Hello, Wenyi. Good afternoon, Alyssa. Good afternoon, Abby. Sorry, why am I pausing? It has nothing to do with Abby or Alyssa. Something just came to my mind. Good afternoon, Erin. Good afternoon, Sharon. Oh well, okay. Good to. Okay. Anyway, good to see you. Hello, Justin. God, see, you guys are exciting me so much. Like it's funny. Okay, I'm going to admit right now, almost every person now. Not only do you have a different way of saying hello or whatever, but now there's this thing where as I'm saying good afternoon or hello to each of you, something is coming into my mind that is specific about each one of you. Like, which is good, right? It means you're human beings. It means I feel like I know who you, I mean, even if my concept is all wrong or something, but like I have like a personal thing with each one of you. I'm realizing it. So I'm going to miss you all when this course is over. But really, like, good job because it's Zoom. So really, like, the more stuttery I'm getting and the less material we ever get to is really a tribute to all of you for being so human. But all right, I'm going to go back. But for real. Okay. But it's making it harder for me to focus. All right. So hello. Wait. And yeah, for example, there's no way that the accent mark was always in Justin's last name. That is definitely new, unless I'm so cold-hearted that I never noticed it before. But all right, I'm just going to keep going. Good afternoon, Armin. Ha ha. I mean, yes. Good afternoon, Yabo, and thank you. Good afternoon, Rachel. That's so nice. All right. Thank you. And you don't have to because maybe you could do research with me. But no, thank you. That's nice to say. And God, I hope to see you in the halls of a building that we ever get back to someday. God, I hope the next time I don't see you people is not at freaking some like virtual graduation. Oh, with that. In fact, I went to a virtual alumni event last week. It was so depressing because virtual, but and in fact, okay, I'm totally stalling, but I have to let somebody in. I don't know if everybody, I don't know if you've ever seen the show The Brady Bunch. Like it was a thing when I was a kid, and it may have revived on YouTube as like a nostalgia thing. But if anybody's familiar, oh, sorry. Okay. Huh. Okay. 1 second. Sorry, there's actually a bunch of things happening in the private chat right now. I apologize. Just hang on a second. And some of them are serious. And I know I made this whole speech about this yesterday, so just bear with me for a second. I'm sorry. And it's not just one person. There's a bunch of people, different things. Hang on. Sorry, everybody. Um, Okay. Okay, things are happening. And I also want to say, wait, I'm going to say in a serious thing, you know, and I hope this doesn't rattle anybody, but this is such a weird year. You know, the number of mortalities that I've been dealing with in my own sphere of life, like I don't even know, was it yet? I mean, one of the reasons like lately I've been wearing ties and stuff. Well, I guess I'm not wearing a tie today, but I've been attending um, a sort of severe number of funerals myself, not anybody too close, but in my life. And many of you are as well, it seems. And I just want to say to everybody in complete seriousness is like, I'm totally sorry. I totally get it. No one ever has to over explain anything about, I mean, mortality is real and is a real part of life. And it seems to be a much bigger part of life this year. And it's a much harder thing to deal with this year for obvious reasons. So just to everybody, like, I know life is still very real and it's more, you know, and you know, also just to everybody, like I always try to say when anybody has a real thing going on, like of course family first and real things before physics, and I do mean that, like, but real things before school for sure. And but can I also say that? Okay, oh I see. Yes, thank you. Okay, cool. Can I also say a weird thing? This came up yesterday because actually I had to go to a Zoom funeral myself yesterday, and I was talking with one of the people there just for what it's worth for anybody, you should always put those things in priority over, in my opinion. But one reason it's nice to have physics in the back of your mind or to know some physics is the same reason that it's nice sometimes for some people to have a religious upbringing, if I may say that, because both of them can be very nice, safe places to fall back on when you're dealing with real issues. And this is not to convince anybody of anything, but just to tell you all in my own personal life, in my darkest hours, certainly I have turned to aspects of my faith and things like that, but I also turn to math and physics in which I have great and abiding faith, in which are all tied up in my faith for what it's worth. Because one thing, just so you know, like I know it, like physics and math can sometimes seem cold-hearted and cruel and seem like math can seem like it doesn't make any reference at all to the human condition. Math can seem like it doesn't, like math equations don't actually talk about feelings or human relations or other humans or life or death. So that's why sometimes to some people they're very alienating, but just for what it's worth, like for me, that's what makes them appealing and safe sometimes, because basically I can do math wrong sometimes, we all can, but math never wrongs me. Like there's no math equation in the world that's ever broken up with me or you know, or divorced me or died on me or anything. Like math never abandons me. I go to math when I want to commute with what is universal, just like the stars are always there, always there. We're looking at this, when we look at the stars, we're looking at the same data set that people looked at 3,000, 5,000 years ago. Like literally, it's like being in the lab with them, looking at the very same data points. I mean, with, you know, some exceptions and some nuances, and often coming to very similar ideas that they came to. Like to me, there is something very beautiful and very universal about math equations and about stars and things that just are what they are. And sometimes for me, it's really helpful to have those kind of truths to fall back on when life seems really messy and really assaultive. You know, when you're being assaulted by life or death, just remember, like the reason I'll always say, fine, don't worry about your exam, worry about what you got to worry about. But the reason I hope that someday you get back to your exam or whatever is because like it's nice to have this crap in your pocket as life goes on, because it's like it's always the same. Like the like, you know, harmonic oscillation is just always harmonic oscillation, and it will just never abandon me, and I will never let me down. There's just, and I can just get better and better at it while it stays still and lets me get better at it. Like that can be very affirming. I just, for whatever it's, I mean, you know, whatever. That's one of the reasons I like math and physics. But I'm just saying that because I'm getting an increasing number of messages from you people about real things that are happening in your life. And by the way, I also appreciate that you trust me with that information. So I don't mean to be, but like definitely my sympathies to everybody, and definitely, and also again, because this is coming up in other classes, I'm sure it's sort of, even though the way I look is a coincidence and it doesn't necessarily mean what you might think it mean about my religion or whatever, but it does by coincidence. But just for everybody too, if you're ever struggling with anything, do not think for a minute that you are not allowed to believe in science and believe in other things at the same time. And do not ever think for, and this is my opinion, and I'm saying it, like maybe it's controversial, but anybody who sets up a dichotomy between the church and the state, between the church and science, or temple and science, or mosque and science, or anything like that, or any stories you've heard about conflicts between, I'm sorry, but for every story you ever hear about some conflict between a scientist and a member of the church or something, there's way more stories, way more truths about all our great science heroes doing what they did in science in the name of the heavens or the deity or whatever you want to, like, I don't want to get too specific, but like, do not think that you have to view them in conflict and that you have to make a choice between one and the other. Absolutely not. And again, this is my opinion, but this I feel so strongly about that I am willing to say it in public. Like, I think it's actually really cruel and ignorant that people make people think that they have to choose between two such beautiful, important ways of trying to make sense out of the universe. And frankly, I really think that anybody who really thinks that religion and science or faith and science or something cannot coexist in the same mind is, in my opinion, probably very ignorant of at least one of those two ways of thinking. And that's why they think that. Like Newton, Galileo, Einstein, almost anybody you want to name was trying to figure out the universe for not coincidental reasons. They did not, most of them did not live. And I'm also saying you have to believe in anything, but I'm just saying being a scientist is about having an objective, open mind. And it's about that you go in with whatever your conjectures are, and you are willing to believe anything. And as a scientist, there's always more than meets the eye, always. And just the thing about being a scientist is be willing to change your view as the data comes in and contradicts it. That's all. Like, yes, you have to keep reshaping your view as more data comes in, but that's it. And that's hard enough. But don't think that the jury is out on, don't believe that. I don't know why I'm getting on this right now, but again, because these are trying times. And in fact, in these trying times, there are a lot of people who keep making it seem like the political climate is like those who believe in science versus those who don't, or saying like, no, or maybe sometimes it's that way, but there's no reason any of these things have to be dichotomous like that. All right, anyway, whatever. Here we go again. Like how many ADHD? Okay, all right. Okay, all right. So that's my rant for the moment. And if anybody ever wants to get me, okay, there's no chance I'm going to do free body diagrams now, is there? All right, let me get back to the material. I'm going to try to do free body diagrams by the end, but if I don't, please remind me. Okay, the thing I want to do now, I want to take, so we did the wave, we've been talking about the wave equation. I want to take the wave equation one more step. I want to analyze these terms like the omega k. I want to get to a thing about wave speed. My goal is, by the end of it, I hope today, to have a concept nailed down that will make you understand why Professor Wu is making such a big deal about the Doppler effect during lab time. I believe he has already begun to make a big deal out of it. He may continue to make a big deal. I was on the phone with him for 4 hours last night, no joke. We were on the phone for 4 hours. Now, we weren't only talking about the Doppler effect, but we were talking for 4 hours last night. And one result of that conversation is, I know where you are in lab and all that, and we all love you very much. Like, in fact, I think we both are sort of agreeing that, especially in the Zoom context, you're one of our favorite classes ever, for sure. And we don't say that to every single class. But one thing I could tell you right now, and it's not always true. Oh, someone's here. Sorry. I could tell you right now, Doppler effect will be on your final exam. Also circuits will be. We'll get to that. But and I'm not going to repeat everything Wu said, but I know what I think he thinks he said, and I know that you have notes, or you will have notes, or you can access the notes, and whatever. I'll do what I can to make them more accessible to you. But Doppler effect is a big deal. I'm going to try to put it in perspective today. No problem. Thank you. No problem at all. Thank you. I'm going to hit Doppler effect from my perspective. My understanding is that he was pretty explicit about it from his perspective. And what we want to say, and this is meant to be a good thing for you, not a bad thing. but because so much time has been spent, we don't want you to think that he's just like wasting your time or off or something like that. It's definitely going to be one of the problems on the final exam. And everything I'm going to try to say today is going to try to put that into focus. So, you know, you still might have to look at the notes later and cross correlate things, but the goal of today is to get to understand the Doppler effect from another angle. Okay, and again, it will be on the final exam, and the professor who loves you and sends his love. Okay, okay, so oh, we're still in this. Okay. Now I believe. Oh wait, I want to make sure that I'm actually talking the right class here. Hang on. Oh wait, okay, so I want to make sure of one thing. I want to make one thing. You in this class, we sorry, I need to make absolutely clear. Did we in this class, did we get up to this? Did you see this page in this class, or am I confusing two classes? I mean, either way, to sit, but did I ever write this down in your class? Did I say this or no? And please be honest. Yes. Okay. That's what I thought. I did think so. I think there's someone missing saying that's what confused me. Okay. Okay. And I believe that's the last thing I said then. Thank you. Okay. Good, good, good. Just making absolutely sure. That's what I thought. It just suddenly I had a freak out moment. Okay. So, and I'm going to backtrack a tiny bit just to remind you why I said that. But right, in this class, what happened was we spent 3 days deriving the wave equation. Okay, actually, I'll rewrite it. Okay, just to review, we spent 3 days with, you know, plucking a string and ultimately concluding but then, right, we found that differential equation from applying classical mechanics to a plucked string. And again, in that differential equation, you know, y, t, and x are the variables. I mean, y, lowercase t and x are the variables. Specifically, y is the dependent variable, lowercase t and lowercase x are both independent variables. But then capital T and mu are both constants. And in this context, they refer to tension and linear density. Maybe to make that even clearer, I could start putting these little serifs on the T to make it absolutely clear that by that I mean tension. I do not mean period, even though that is going to come up today. So be careful, right? But so we concluded that. I'm just changing something on the screen. We concluded that from applying Newton's laws to a plucked string. But then we also reminded ourselves from writing out a collection of phase staggered oscillators, from writing that out as y equals a cosine omega t plus kx, right? Which we had independently said like a month ago, right? We just said, oh, if we picture a bunch of oscillators staggered, then we write cosine omega t plus kx. Now that we have the skill of taking partial derivatives, we we partial differentiated that equation twice, once with respect to time, I mean, twice, 2 times. We differentiated it twice with respect to time. We differentiated it twice with respect to space. And then we like put the two things together and found this thing on the bottom, which says a lot. It says two things. One, oh my God, okay, that cosine thing was a solution to this differential equation, meaning, oh yeah, like no matter how we look at it, it really looks like waves are described by this second order partial differential equation. Like whether you just want to mechanically look at a piece of string or you want to build up a wave from a bunch of bouncy things, either way, it ends up being this second order partial differential equation, which is like sort of exciting. It sort of just is that much more evidence for believing in this way of talking about waves. But then also, this is just like what happened to us at the beginning of the year with the beginning of the semester with simple harmonic oscillation, in that like this is like the line between physics and math. Physics of one type gave us this top equation. Physics of another approach gave us the bottom equation. They look like different equations because they have slightly different physical information in them, or at least in the constants. But if you back up and look at the mathematical form of these two equations, it's exactly the same form. It's second time derivative equals constant times second space derivative, both ways. And since they're both evidently describing the same phenomenon, I mean, it seems more than reasonable to believe that, and in fact, it's definitely reasonable to believe that since these are two identically formed equations describing the same phenomenon, and the only thing that's different about them is the details of the constant, this is where we concluded last time, it must actually mean that these two different combinations of constants are merely two different names for the same thing. I mean, this is just like, so here, now again, I mean, I know I just said this like yesterday, but I'm just backing up to try to make it clear why I'm saying it. And again, I'm writing the K in a funny way or I'm being a little bit inconsistent about that. Oh, no, I'm not being inconsistent. I'm writing this K in a funny way to try to make it clear that I don't mean, I mean, it's an unfortunate coincidence, but I don't mean the same K as the one that's up here in blue. That K up in blue is the one from Hooke's law. This K, and I'll write it again in a second, is the angular wave number K, the K that's in, well, I'll write it again in a second, but they are two different Ks. Similarly, the T that I'm talking about here is T for tension, not T for period. So I'm just trying to distinguish by putting the serifs on, do however you want in your, in your notes. But what I'm coming to conclude is, well, if I have two different, I'm coming to conclude exactly what I've now said 400 times. Like, it must be the case that omega squared over K squared is one name or one way of understanding some constant number that could also be understood as the ratio of tension to mu. So I think there's information there to extract or to unpack. That's what I want to do now. Like, what's the there's implications of this, I think. And the way to see the implications is, let me unpack the left side first. The omega squared over K squared, especially because I believe that K, again, this kind of newish K that came into play in lab 3 and came into play in the collection of staggered oscillators, that K, like it's the newest thing. It's still confusing to some people. Let us look at what it means and what it means in this context now. So oh, wait, sorry. Okay, just to remind you, and also to get the notation straight, like what was omega in the first place? Omega was angular frequency, right? Which means how many cycles we're doing per second, but not measured in cycles, measured in radians, right? It's how many radians we're passing through seconds, remembering that there's 2 pi radians for every cycle. So omega, first of all, was measured in radians per second. Like whenever I put things in brackets, I'm talking about units, right? So omega was measured in units of radians per second. It meant 2 pi over capital T. Now the old T, not the T with not tension, but T meaning period, right? And remember, period was time for one cycle. So strictly speaking or whatever, period is measured in units of seconds per cycle. But again, in the back of our minds, remembering that cycle is not really a unit. And in fact, even radians are not really a unit. They're really dimensionless, right? But if we're just trying to bookkeep here, omega is like in radians per second. Period, T period is in seconds per cycle. And it's reciprocal standard frequency F, which I'm writing cockamamie on the side, the reciprocal of period, standard frequency is measured in cycles per second. I'm reminding you of that. And again, really like back from the day from harmonic oscillation, what I'm really saying, I mean, it's always sort of confusing and hopefully sort of clarifying. Like it's really 3 different ways of looking at the same quantity, omega, F, and T. If you have any one, you automatically have the other 2. They're all ultimately interchangeable, but the reason we have all 3 of them is that omega is what explicitly pops out of and is embedded in the math. Omega is like radians per second. It's the most mathematically explicit and easiest to work with. But on the other end of the spectrum, period was the most experimentally observable and measurable. Like it's very hard to measure radians, and it's very hard to even think in radians, even if you are a physicist. In the lab, what we can think of is how much time does a cycle take, and we can measure that with a stopwatch. So we've got period over here being the most experimental, measurable, observable quantity, omega over here being the most mathematically useful quantity, and the bridge between the 2 is standard frequency, right? So omega ft, that was like our universe in the universe of simple harmonic oscillation when things were just cycling back and forth in time. We could talk about them with omega or with F or with T, right? That's like a reminder. But now let's look at the space piece of all this. Like now we're not just talking about oscillation anymore, we're talking about wave pulses. So whatever they're doing in time, they're also equivalently doing in space. That's the beauty of it. So in space, we introduced an equivalent, right? And again, it always seems a little bit more abstract. It gets introduced later in the course, but it really is analogous. And by it, I mean K with serifs, the angular wave number, the thing that came up in lab 3. In other words, I'm talking about this, reminding you. So I'm unpacking K again, just to remind us all. So recall that K, which again, I'm writing in this weird way because I don't, and here's where, like, I know I'm going to, like, there's always someone who, I'm not talking about the K of Hooke's law, whoever you are that is now paying attention. This is not the K of Hooke's law, even though it's all related. This is the K known as angular wave number. And what was that? Well, I just want to be equivalent in the way I'm doing this. Right. That, well, it's measured in units of 2 pi. It's measured in units. So I'm being a little bit inconsistent here, but K was not measured in units of radians per second. K was measured in radians per meter, right? It wasn't the number of cycles per unit time. It's the number of cycles per unit space, literally, right? And so if we want to write that in notation that's consistent with the other, we could say that it is 2 pi over, now what over what? Okay, not over the full, like over here I said omega is 2 pi over T. It's number of radians per the amount of time for one cycle. Here I want to say number of radians per the amount of space for one cycle. So do we have a symbol for that? Well, yes, we in life do have a symbol for the amount of space for one cycle. I don't know if we, I mean, and you may or may not have used it in lab, and you have definitely used it in other science courses, but I've never mentioned it here. So I want to be explicit about it. The spatial equivalent to period, the spatial equivalent to T is lambda, as in wavelength, right? Again, I'm introducing it now for the first time, but I'm introducing it in a denominator. Like T meant period, means time for one cycle. Lambda, so lambda, by that, I just want to be as consistent as I can. Yeah. So lambda stands for wavelength. Of course, you've heard of this your whole life. And it literally does mean exactly what it sounds like it should mean. It means the length of a wave, but not the length of a whole wave phenomenon, the length of a given wave pulse, meaning the length of one cycle of the wave, meaning the length in like the number of meters from one crest to the very next crest, or one trough to the very next trough. Exactly what you think, I think, and exactly what you probably thought in 6th grade, but just putting in perspective now. So lambda is wavelength. It means the distance for one cycle. What I might call crest to crest or trough to trough, or but actually, since you're scientists, all of you, like in a lot of medical contexts, or I even remember this when like my children were being born, like they often call it peak to peak, like in hospitals and stuff. The peak to peak length is wavelength. And it is definitely, am I running out of room? It's definitely right. And lambda, the units of it are meters per cycle, right? And cycle isn't really actually a unit. So ultimately, when you talk about like the wavelength of light or something, you'll talk about, you know, like 7 times, I'm sorry, you'll talk about like 1 times 10 to the -7 meters is like the wavelength of the color red or something. And it's technically, you're saying that many meters from one peak to the next peak, what that number of meters per cycle. So that's what wavelength is. And what's wait in the parallel? Oh yeah, and there is no, and I guess, and there's no completion to this analogy. Like, so, there's no, I don't know of any equivalent of standard frequency of f. I don't know what hertz would be in space. But what I'm trying to say here, the key thing that I'm trying to say here is, K is always a little bit more abstract and confusing to people than omega. People, because you have a lot more time to get used to omega in the class than K, but they are literally analogous. Specifically, what I really specifically want you to see, what from here on in, whenever you think of omega, this, I think that's the most direct visual picture of omega. It's, radians per time. It's 2 pi over period. That's what omega is. And similarly, then the exact analogy is K is 2 pi over space, 2 pi over wavelength. Okay, so omega is 2 pi over period. K is 2 pi over wavelength. And wavelength we designate with lambda. Okay, I hope this is clear so far. Wait, something just happened to my screen. Excuse me, one second. I think you're still there. I hope you're still there. Wait, I think you're still there. Are you still there? Wait. I'm losing everything.
We're still here.
Oh, okay, good. Thank you. So, apparently my computer is made of the same ADHD material that I am, which is that like it gets a text and then everything like crashes. Like it's like my computer can't even handle it. All right, anyway. Okay, thank you. Yes, you're still here. So omega is 2 pi over t. K is 2 pi over lambda. Why do I care? Why am I saying all this? Well, because then I can say if that's true, thus oh, wait, good question. Okay, in the private chat, there are functions of it. I'm not going to mention names or whatever, but good question in the private chat. So, someone just said in the private chat, are they functions of each other? I am saying I like that language too, by the way. I am saying that omega is a function of t, you could say, and I am saying that analogously, K is a function of lambda. I'm not actually meaning to say that omega is a function of K or the other way around. And again, this is a very good question, whether it's like posed as an assertion or a question. And again, I want everybody to understand, and this would count to 75 points or whatever, that it's still relevant to you people, in that, like, even if the person just asked, so someone just asked, are they functions of each other? Even if they're thinking the answer is yes, and I'm saying the answer is no, please everybody understand that makes the question just as legitimate, right? Like that's utterly clarifying to point out that omega is a function of time, K is a function of space. They are independent functions though, just like lowercase t and lowercase x are both independent variables, which is a very powerful term, especially now that we have two of them for the first time in our life. And that's why I'm glad for this question, and it's worth pausing on for a second. For the first time in our lives now, in our math physics lives, we have two independent variables, lowercase t and x. And when I say they're independent variables, I actually mean two things. I mean, one, that each one of them is the independent variable for y, for the dependent variable of y, but also I literally mean they're independent of each other. And that's why you can make two separate graphs in lab 3 and all of that. So what I actually want to emphasize here, whether this is, harmonious or dissonant with what the person was thinking, like omega and K are like independent constants. They are not related. I mean, they're related, but they're not functions of each other. You could tweak one without tweaking the other while you're making a wave. And that's like actually a super important property of the wave. And I'm going to show you another way to see that in a second. But so I hope that answers the question, but it's a good question. But what I am going to, but it doesn't mean I can't put them together. Right. And in fact, and this is the subtlety of math and physics. Like I'm about to put omega and K together to look at something, so I can certainly relate them. I'm just saying when I relate them, I'm going to be relating to independently tweakable quantities. Now, when I put them together, so it's kind of like distance and time are independently tweakable, but then you put them together and you get this something called speed. Well, that's exactly what I'm going to do here. like by definition, omega, we just said, but I hope that does answer, is 2 pi over t, right? And k, we just said, is 2 pi over lambda. So if I put them over each other like this, then I get, I mean, this looks like so messy and awkward because it is, but when you divide by a fraction, you multiply by the reciprocal, right? Like 1 divided by 1/4 is 4, because in fact 1/4 goes into 1 4 times. Like it actually does make sense. So you can clean this up any way you want, but I claim, please check, like do it your way, but check. I mean, I think you get this, right? And then that means what you're getting is, now, I don't know if that makes it look messy again, but it's in English now, so it's meant to try to clarify. What I'm saying is, sorry. What I'm saying is, oh, wait a second. When you put omega over k, what you're really talking about is like the wavelength over the period. You're talking about the length of the wave over the time of the wave. Literally, you're saying, like, if you had this wave, like you're standing at Coney Island and you're watching water ripples come in on the beach, if you knew for a fact that each ripple was 3 meters from the next ripple, right, like each wave crest or whatever you want, each wave peak, if you knew for a fact that they were 3 meters apart, i.e. that lambda was 3, and if you knew for a fact, because you had a stopwatch or whatever, that when you had, each time you had to wait for the next crest, not only did you have to wait for 3 meters to pass, but you had to wait for, say, 2 seconds on your stopwatch, then what you're saying is you have to wait 2 seconds for the phase of the wave, for the crest of the wave to travel 3 meters. In other words, crests are traveling at 3 meters per 2 seconds, like 1.5 meters per second. Like what I'm saying is this is the speed of the wave, like literally and fully. Omega over k is lambda over t, which you could put one final way that you might recognize from chemistry. In other words, omega over k is the same thing, just by definition, as lambda over t, which, if you want to put it another way, not to confuse things, but actually to put it the way that is most commonly seen in most science books, that's the same thing as lambda times frequency, right? Or wavelength times frequency. But actually, it might be better than that. I mean, yes, that is what I'm saying, but let me just give it. Such a bad person. This is too important to not do right. This is a big deal. Now I'm saying, no matter how you write this thing, whether you say wavelength times frequency, which is really the way you're going to see it the most, well, definitely the most with Professor Wu, the most in chemistry textbooks, like PChem, the rest of your life, you'll even often in chemistry books see it written as c equals lambda f, where c is the speed of light. That assumes that light is acting like a wave, and we're not saying that yet, but I'm not saying it's not true. But the point is that for any given wave, For any given wave, the speed of the wave is its wavelength times its frequency. That's a common way to say it. That's just the same thing as saying it's its wavelength per its period, which to me is the most intuitive. Like we're just saying speed is distance per time, the distance of a cycle divided by the time of that same cycle. But the most relevant, but I'm saying all that because here, what that then means is that speed is omega over k. And remember, omega over k like popped up in the wave equation a second ago. So that's what I want to go back to. So first of all, this is important. But before I go any further, let me really stress exactly what this is saying. I'm saying, however you write it, omega over, and please do know all those three different expressions. Like they all have a use, but they're all in the end ways of saying propagation speed of a wave. And I mean propagation. Let's be very clear. A wave is a collection of staggered oscillators. Like if you're having a pulse ripple past you on a horizontal axis, the way we understand that is you have a bunch of little particles that are oscillating continuously on vertical axes, right? Now, each one of those particles is like a little x equals a cosine omega t. Yeah, each one of those particles is like a little x equals a cosine omega t. Each one of those particles, like you can take derivatives like we were earlier in the year and solve the differential equations. Like for each one of those particles, if you say x equals a cosine omega t, you can differentiate and say therefore v equals negative a omega sine omega t, right? And like you differentiate again in that acceleration, and that's how the Hooksaw thing works. But that kind of velocity, I just want to like be as clear as possible. When I say that when I talk about v like you did on the exam, like with the pendulum and everything, when we say that v equals dx dt equals negative a omega sine omega t, we're talking there about the individual instantaneous velocity along like the transverse axis of any one of these countless oscillating particles. That v is like a thing. It's important to all the math. It's important to the ingredients that we're using to build up the wave, but that is not what I'm talking about here. What we're finding here, when we talk about wavelength divided by period, we're talking here about the speed at which the pulse actually propagates along horizontally. Like this is the speed not of any individual thingy thing. This is the unthingy speed. This is the speed at which the wave waves, like, you know, the speed at which sound gets from my mouth to your ears is the kind of speed that we're talking about here. And remember, when I talk and something goes to your ears, remember, even though the only things that are moving are air molecules, there's no air molecule that's going from my mouth to your ear, I hope. And so the speed we're talking about here is not the individual speed of air molecules. It's the speed of propagation. And it looks like it's a very easy equation to get it. And it is. That's already kind of exciting. Like, so here's like, so this is like this is the unthingy speed, so to speak. But it's real. I mean, it's calculable, it's reliable, it's predictable, we can use it in other equations and stuff. But also notice that it's a speed, it's not an acceleration. There's a reason for that. So from now on, when I use V, I mean propagation speed. Like unless otherwise specified, if I'm talking in a wave context and I say V, I mean the speed at which the whole wave actually, like the whole pulse actually propagates. That's what I'm talking about, right? And I'm saying that can be expressed as apparently as omega over K, because even though that looks abstract, omega over K is a fancy way of saying wavelength over period, which is also a way of saying lambda times frequency, which is what you have to use in all the Doppler effect things for Professor Wu. Okay, but we're talking about wave speed. But now, if we understand that, then well, okay. Okay, this to me is a very big deal. Okay, I mentioned God before and all that, and I mentioned death. If I'm going to mention all these things that are in my soul, I have to mention this. Like, why I think it's a big deal that omega squared, like, okay, omega squared over k squared, according to all this analysis, or just according to like playing with definitions, equals v squared. That's already sort of nice because it gives us a glimpse. Oh, we can figure out like the wave speed of like a wave or something. But if going back to our differential equations, right? If we're trusting now, not only that omega over k equals v, or in other words, omega squared over k squared equals v squared, but if we're also trusting that evidently omega squared over k squared was just another way, was equivalent, or another way of finding the same constant, which is tension over density. And if we really believe all this stuff, it means all the units should even work out, and they do, but you should check on your own. I'm not going to do that right now, but it doesn't even look like they should. But if you're careful and work out the units, you will find that the units of meters over second are the same as the units of newtons over kilograms per meter, which in fact, even as I say it like that, makes it even sound more like the left side, I'm sorry, meters, like the left side is meters squared over second squared, right? Like speed squared is meters squared over second squared. The right side, tension over mu, which looks like totally doesn't look like it should be related at all. Tension is a force measured in newtons. Newtons are kilograms times meter per second squared. Mu is density measured in like one-dimensional linear density. So mu is measured in like maybe you can write this down or just check it. You'll check it if like, I mean, you should. Tension is in kilograms times meter per second squared. Density is in kilograms per meter. So the kilograms cancel out and the meters flip up, and you have meters squared per second squared. The units are the same. And that means, okay, number one, it means, oh, then I guess T over mu is another expression for V squared. Yes, I mean, that's true. But it also means like tension, and it also means, thank you for coming to my bar mitzvah. Today I am a man. Just kidding. But it means that the that the speed is dependent on two material properties of, in this case, the string that we set up, or more generally, whatever medium we set up. Tension and density are parameters. They are constants, not because they are mountain given constants, not because they're like Planck's constant or pi or something. They're constant to the extent that the medium has constant material measurable properties. In this case, how tight the string is and how thick, how dense it is. Once you fix the material properties of the medium, apparently you have fixed the speed at which pulses propagate through the medium. This is huge. Like really, like let me say it a different way. Like really, really, it's huge. I mean, it's huge. Like back up and remember, for a simple harmonic oscillator, we did stuff and we got, we finally found that like omega equaled square root of k over m. But we found it for the same process that we found this stuff here. But then we reminded ourselves K and M were parameters. They were material properties of our mass spring system. And what we inferred from that, we noticed like, oh, so the rate at which an oscillator oscillates, like the rate, its frequency, the rate at which it wiggles back and forth is totally determined by the ingredients of that system. Like once you know how tight your spring is, and once you know how heavy your block is, it's going to vibrate back and forth at a certain rate, regardless of how far back you start off by pulling it. Like in other words, frequency was independent of amplitude for our original oscillator. Frequency depended on material properties of the setup, frequency and thereby period depended on the ingredients of the system, not the initial conditions of the system. It didn't matter how far back you pull the thing or how close you pull, it would still wiggle back and forth in the same rate. Hence, harmonic oscillators are clocks. They keep time independent of space. I mean, I think, and like, so Galileo's pendulums in the chandeliers in the Sistine Chapel, like wiggled back and forth at a given tick-tock, whether they were making long, slow arcs, long, fast arcs or short, slow arcs. It worked out the same, conjectured Galileo and tested Galileo with his heartbeat and so forth, and hence clocks. Now we're saying, wait, the same logic seems to apply here. You set up a medium through which you're going to send pulses. Like you set up your string, it's a string of certain amount of density, and you tie it to both ends, so you give it a certain amount of tension, and then you shake it. Well, you can shake it a lot and make really high frequency wave pulses. Like you can make a lot of pulses. You can generate a lot of pulses per unit time. And so you could send out a lot of crests per every second, or you can you can set a different initial condition and shake slowly, you think, so you get fewer crests per unit time. In other words, you can play with the frequency, sure, just like you can play with the amplitude of an oscillator. But as long as that medium is fixed, you can do nothing to the speed at which each one of your pulses propagates along. If you shake hard, you like. So now, in other words, what I'm saying is, if again, there's many different ways to write speed, right? On the one end, I wrote it as omega over k, so I could prove this point or show this point. But now I'm going to write it as lambda over f, just because that's more common, more intuitive in a way, and it's the one you use in lab. If I think of speed as wavelength times frequency, you can play with the frequency. You can make a lot more waves per unit time, but that you cannot play with the V. The V is fixed by the material properties of that medium. It just, once you know it's a string, the V is done. And therefore, if you shake a lot and up the frequency, necessarily the wavelength will go down. You'll get shorter pulses. If you shake less frequently, you'll get longer pulses. And you might say, well, that's obvious. Yeah, I see that equation, V equals lambda F. I mean, if the F goes up, the lambda goes down, like duh. No, not duh, right? Like think about it like F equals MA. You could say duh, if the A goes up, the M has to go down. No, that's only duh if you hold the F constant, right? I mean, think about linear equations for a second. They are nice and simple and reliable, but they can be done anyway. In fact, this is why people always like tank in chemistry if they're not used to this. Like F equals ma, you could say that means the bigger the mass, the smaller the acceleration. But that's only what it means if you assume a constant force. Yes, if I push two objects the same way, the heavier object will accelerate less. But you can look at F net equals ma a totally different way. You could say, what if I hold the mass constant? Then I have two bricks that are, the same mass. If I push one harder than the other, then the one I push harder will accelerate more. Like F and A are directly proportional if you hold M constant. Or you could hold A constant. You could say, I want two objects both to fall at 9.8 meters per second squared. I want the acceleration to be constant between two objects. What should I do? Well, apparently, if you make one of the objects heavier, it'll work because that heavier one will be pulled harder by planet Earth. In other words, with F equals ma, you can hold any one constant you want, and then the other two adjust to that. If you hold A constant, then F and M are directly proportional. If you hold F constant, then M and A are inversely proportional. I'm not trying to yell, but I am trying to yell because this gets totally missed all the time in life at cocktail parties that I'm not invited to. So even simple linear equations that have just like three terms in them, they're still like fun and full of possibilities because you can hold any one thing constant in general in life with linear equations. But here, with V equals lambda F, if you think it's obvious that and it is treated as obvious, again, it'll come up a lot in PChem and stuff like that. Yes, when F goes up, lambda goes down, but that's because you're tacitly already assuming that V cannot be tweaked. And the thing is, that is true. But the fact that first of all, that is true. Like it's right to assume that. But whoa, you better realize that that's what you're assuming when you do that. But two or B or whatever, that's an enormous revelation. That means that waves always travel at one given speed as long as the medium is fixed. That's unbelievable. That's why we love waves. Let me elaborate even further, just because I'm going crazy. Like what this actually means, among other things, and I often say this to like my 6-year-old son when he's 6 years old. Like if you're standing at a pond or something, and there's ripples in the pond, or you're standing at the lake and there's like waves in the lake, or Coney Island, whatever. If you, or just any situation where you just see normal everyday waves, you don't have to make a measurement. You don't have to know a lot about numbers. You don't have to be precise. Just watch those wave ripples for a little while, and you'll realize something about the wave ripples that everybody takes for granted in drawings and stuff, but it's actually kind of a big deal. If you look at the wave ripples for a while, I mean, this is what I always say to my son and then my wife, is I was like, wait, what? One thing you never notice one ripple catching up to another or crossing it or overtaking it. Like you can see two ripples going in opposite directions and crossing, and that's very interesting, and that's called interference. But any ripples that are traveling in the same direction, the reason waves look like all one big wave phenomenon, the reason we all sort of recognize waves and they're sort of, I don't know what, calming or whatever, is but you just don't, I don't think people consciously think about this, but they just unconsciously know it, is that ripples never catch up to other ripples. They don't even try. They don't even ever shrink the gap or loosen the gap at all. The gap between two ripples remains constant because all the ripples necessarily go one in the same speed, and they don't speed up or slow down even as a group. Now, like once you fix the medium, in the case of water, that means fixing like the depth of the water and the salinity of the water. I mean, sure, if the ocean floor starts getting deeper and deeper, or like there's a lot of salt in the water over here, like that affects the medium. But or like air, everybody talks about the speed of sound in air at, and they talk about it like it's a number, 340 meters per second, because it is at standard temperature and pressure. But like, why can we even say that? Why is there a speed of sound? Why, like, there's no speed of baseball. There are speeds past which baseballs don't tend to go, but like I throw like a 75-mile-an-hour pitch, and any one of you in the class probably throws like a 95-mile-an-hour pitch, and Nolan Ryan threw like 120, like, and baseballs go all kinds of different speeds. They don't just automatically go a given speed, but apparently sound goes a given speed, as long as we specify, and it goes a different one in a different medium, like the speed of sound in water is different from the speed of sound in air. But once you say air at a standard temperature and pressure, it's not just a rough approximation, it's damn reliable. Like the sound will go at 340 meters per second through that air, and that means each ripple will, and no ripple will catch up to another ripple, and no ripple will speed up, because the speed of propagation is, so I'm saying, not to say, this sentence, I mean, if there's any takeaway in all of this, it's this sentence. And even this sentence has sort of two things going on in it that I now want to emphasize. And I am watching the time, but this is like the point of today. Maybe, God, I will do the free body diagrams, and please remind me again on Monday. I don't want to do that because like I don't want to confuse. I don't want, God forbid, anybody would go away thinking that that free body diagrams apply to this somehow or something. So, but I do appreciate the reminder, and I would love one again. And I do apologize for not doing it yet. But so this sentence, which again, for any of you who's paying attention, if you're noticing that I'm getting all hot and bothered about this, it is one of my, it's a huge point in physics. It's a huge point. And like all points in physics, it might sound sort of obvious once we're saying it. I hope it almost sort of does, because I am certainly trying to argue that it makes sense. I am certainly trying to argue that once you know enough about waves, then you would have to see that this would have to be true. Like it couldn't be any other way. This isn't just a discovery that somebody made in the lab, and that like with advanced technology, 40 years from now, someone else is going to discover that, that it was wrong. This is analytical, right? I'm saying this, by definition has to be true if all of the pieces that we're looking at logically are in fact true. So in some sense, it may sound obvious at this point, but besides the fact that it's really powerful and important, also there's a subtlety even in this sentence that I want to spend my remaining time emphasizing. So this sentence here says, okay, for any and every given wave pulse, the speed of propagation is fully determined by and constant relative to the medium. So there's two parts to that sentence. Okay, I mean, first of all, the key to this whole thing is medium. I am saying that you fix the medium, you fix the speed of propagation. If you know the medium, you know the speed of propagation. That is certainly the overarching point I'm making. That and conversely, if you tweak anything besides the medium, you do not tweak the speed. You cannot play with the speed of a wave except by playing with the medium for that wave. So this is another way to see how intimately tied together a wave is with its medium. Remember, I said sort of a month ago, the medium is not just like the fog through which the wave sort of happens to be annoyingly passing through. Like the medium is not just like an obstacle to the wave. The medium is the driving mechanism for the wave, so much so that if you change the medium, you change the speed of the wave. That's like one big point that I'm trying to make. And again, what's my proof of is that T over mu equals omega squared over K squared, like that. Oh, and in fact, before I get to what I'm really saying in short is the ultimate way to write the wave equation, like hence, like if you want to mathematically put all this together, what I'm really saying is this. Like that is the wave equation. Like T over mu is one way to write it when you want to prove it in a Newtonian way. Omega K is another way to write it if you're like solving differential equations. But this, and sometimes you'll see that V written as a C if you're talking about light waves, but this is the wave equation. And if you really, I mean, that is an extraordinary amount of information packed into one sentence. I mean, to say that, like that summarizes everything that is relevant to or implied by any wave pulse that that at any given moment, and at any given point in space, at any given point in time, the acceleration is directly proportional to the concavity, and the constant of proportionality is the square of propagation speed. Like that's like every property of the wave is there in that one freaking equation, and yet it's just a linear equation, like with a slope of v squared. It's a phenomenal. I mean, if you're ever going to like equations, that's one to like, I think. But and that's the way it's generally written in books. But the other thing I have to emphasize in the 4 minutes we have left, I think, is don't forget about Galileo's principle of relativity. Galileo's principle of relativity, specifically form number 4, by which I mean there's thousands of different things to call this in different ways. Never, and you'll see this. Well, you already did see it with Wu. You'll see it again. Like, never forget that all velocities are relative, right? Velocity is a relation between two objects. It is never a property of one object, right? Like the Earth doesn't have a speed. The Earth has a speed relative to the sun and has a different speed relative to us, and they're both equally legitimate. The laws of physics are the same in all inertial reference frames at all different velocities, right? So my speed relative to the Earth is 0. My speed relative to the my speed relative to the Earth right now, assuming I'm sitting, my speed relative to Earth is 0 miles per hour. The Earth's speed relative to the sun is 65,000 miles per hour. Therefore, my speed relative to the sun is 0 plus 65,000 equals 65,000, right? And all those numbers are equally legitimate. All speed depends on what you compare it to, right? The speed of object A depends on what object B you compare it to. And as long as object B is not accelerated, then any object can be used for comparison, and they're all equally legitimate. Like, in other words, the Earth moves and we don't feel it. That is Galileo's principle of relativity, the cornerstone of physics. It still applies here. it applies to particles as well as it does to pulses. A mathematical way of putting it, just to remind you, because again, this totally plays into the Doppler effect, or you already see it. Like, don't forget that in general, for any velocity that you're ever talking about, any velocity of some object A relative to some other object, call it C, is necessarily the velocity of object A to B plus the velocity of B relative to C. Like, even when one of those terms is not zero, even when we're extrapolating to 2 or 3 dimensions, like that always holds true. Velocities add like vectors, right? That's why you take subways, because the velocity of you relative to the subway might be 0, but the velocity of the subway relative to the streets is 100. So the velocity of you relative to streets is 100. Now, why am I saying this? Again, I'm going to pick up on this next time we meet, but this is still true even with waves. Like, relativity still means that whenever you're talking about the speed of something, it's always relative to something. Well, with a wave, when I say that the speed of a wave is fixed, I mean it's fixed not only by the medium, but it's fixed to the medium. When we say, and I'm watching the time, I promise, when we say that the speed of sound, when we say the speed of sound, and this is a realistic good number to know, that the speed of sound at STP, sound in air at STP, at standard temperature pressure, is approximately 340 meters per second, which is a little bit less than 1,000 miles an hour, right? Like, that's a real number. What we mean is that sound necessarily has to propagate not only through, but relative to the air at 340 meters per second. It doesn't mean that sound has to go 340 meters per second relative to a human being. It doesn't mean relative to the ear that receives the sound, or relative to the mouth that sends the sound. It means that the minute sound goes out of your mouth, it must immediately be traveling at that speed relative to the air. Now, that is still relativity, but that's very different from a baseball. Very different, right? Quick, I have 1 minute. So let me just to put this in focus. And again, I think you already saw this with the Doppler effect, but like, if I can throw a 75 mile an hour pitch, that means if I get on top of a train that's going 100 miles an hour past you, and I throw the 75 mile an hour baseball relative to me, that means you standing on the platform see, sorry. Yes, totally. Awesome. Yes. And I will let you all go in a second, but that's awesome, person. Yes. If I throw, wait, actually, I better make sure I actually read all the words except for the last, maybe the last word was, oh, well, yes. Right. So exactly. So, and this is the last thing I'll say. I know it's like 129 and a half, but like, check this out, because this is so weird about waves. Like, it's not weird because it's completely consistent with every physics law, but it makes them so special. If I stand on a train and I throw a 75 mile an hour pitch off the 100 mile an hour train, remember, again, all speeds are relative. So if it's 75 relative to me, but I'm on a train that's going 100, relative to you, that means that the ball goes past you at 175 miles an hour. And it's no surprise, like, you knew that already. But more specifically, meaning I don't like catch up to the baseball. It's always 75 miles ahead of me every hour. And since I'm going past you, then the baseball is always 175 miles an hour past you every hour. Like, not surprising, but that's not how sound works. If I shout off the train, the sound goes out at 340 meters per second relative to the air, not relative to me. It doesn't care what I'm doing. It will go 340 meters per second relative to the air. So if you're standing there on the ground, like standing in the air, you'll see the sound go at 304, or hear the sound go 340 relative to you. But what's it doing relative to me? If I'm rushing toward it as it came out of my mouth, if I'm rushing toward it at 100 miles an hour relative to the air, then the sound is only going to go 240 meters per second relative to me. In other words, take it to an extreme. If I start going closer and closer to the speed of sound, I literally do start catching up to my own sound. You can't catch up to a baseball that you throw, no matter how fast you're going, the baseball goes away from you. But if you go at 339 meters per second, while you're making sound, then the sound only goes 1 meter per second ahead of you. If you now get up to the speed of sound, you will literally catch up to all those pressure pockets that have been catching up to each other. And you can literally then go faster than them and pass them and break through that wall of sound, i.e. that sonic barrier, i.e. that's what a sonic boom is. Like, you can catch up and pass your own sound. You can even slam on the brakes and back into it, and you'll hear the sound backwards. Like, how fucked up is that? Excuse me, I'm sorry. But that's how different waves are from particles, even though they're following all the same rules. The fact that their speed is fixed to the medium changes the whole game. And it's why there's things called the Doppler effect and all that stuff. That's okay. I went a little bit over. Sorry, got a little excited. Excuse my language. I should never say medium again. But no, but like, I hope you get it. And we'll talk more about it on Monday. But and I have to go pick up my kid and blah blah blah. So if I can get a goodbye, but sorry to get all excited. But are we good? Goodbye. Hello.
Bye, Professor. Thank you.
Thank you. Thank you. Bye. Bye. Awesome. Bye.